Well, good evening and welcome to Space Oddities. I hope you're all well on this Tuesday evening. And I'm joined by some familiar faces. How are you, Roger?
Fine, thank you.
Good. Daz?
Lovely, thank you. Lovely, thank you.
Michael, you okay?
Yep, fine, thank you. Wonderful.
And Lou?
Peachy?
Peachy.
Peachy.
That's a lovely English expression.
Yeah.
Anyway, welcome to Space Oddities. If this is your first time here, you are most welcome. And if it's not, you're still welcome. So thank you, first of all, for your donation so far this evening. Very kind of you, much appreciated. All the money going to keeping us on the air, as it were. So I hope you all had a fantastic week. We've got quite a packed program tonight, as usual. Tonight, we're going to be looking at gravitational waves. We've looked at them before, but I just wanted to just update everything as far as what's going on in the science of gravitational wave astronomy, what's coming up, what have we discovered, that sort of thing. Lou's going to be talking to us about the exploration of Jupiter because we've got two spacecraft on their way to the Jovian system at the moment, America's Europa Clipper and Europe's Jupiter Icy Moons Explorer, or JUICE. Not getting there for a few years yet, 2034 and 2035 respectively, but well worth waiting for. A few years to go yet. But Lou's going to tell you all about the exploration of Jupiter from space. So got that to look forward to. We have the usual suspects. We have, of course, Einstein of the week, our regular rummage through the sewers of social media to see what people have been saying this week about the universe. And we've also got Constellation of the week. And Roger is also going to be doing his three things that he couldn't last week because he was miming all the time and decided not to mime this week and actually say something. So he's auditioning for the part of Marcel Marceau in the local amateur dramatic society. So yes, there you are. Stop it now. Actually say something this week. So we've got those to look forward to. And on Sundays, I'm afraid I haven't done the news for this week. I just haven't had a chance. Been really busy this week. So I'll hold the stories over to next week. So you will get them. A couple of things I wanted to discuss that have been in the news, particularly with relation to Lou. You may remember that Lou recently gave a presentation about the Hubble tension, about the discrepancy regarding the acceleration rate of the universe, which differs depending on what method you use. And it's since been announced, although yet to be confirmed, of course, because this is science, that the James Webb has enabled astronomers to do some pretty close calibration of the distance to ancient supernovae. And they've come up with new distances thanks to the incredible accuracy of the James Webb Space Telescope. And now it looks as if the measurement using supernovae and the measurement of the expansion rate of the universe using the cosmic microwave background actually come out about the same. So the Hubble tension appears to have evaporated. What do you think about that, Lou?
Well, I think that it is interesting. I think it is a single study. And I think I'm aware that although the values for the Hubble constant are now much closer together, they are not by any means identical. So perhaps a little more work needs to be done, but this is a very interesting finding. I was consulting with an galactic astronomer friend of mine recently. He had not heard about the latest research, but he said it sure made sense that it would happen with James Webb Space Telescope. So let's see if that can be replicated. I think that's what you do in science, right?
Yeah, absolutely. Yeah, I mean, as I say, it is only one study and it's yet to be confirmed by other studies, but so far it's holding up.
The other question I was asked is, since you can use the Hubble constant to back into the age of the universe, someone asked me, well, so what's the age of the universe now? I said, well, I haven't really worked it out.
Interesting. Yeah. But, I don't think people fully appreciate the precision with which the Webb telescope is measuring things.
Right.
It's giving us a level of precision we've never had before with any telescope, because of the advances in technology and the incredible engineering of the Webb telescope.
Excuse me for just a moment. I'll be.
Okay. All right. So so Lou will be rejoining us shortly. He's gone to sort a car out, I think. Anyway, there we are. The other thing is that on Thursday there's going to be a landing on the moon by the Japanese Resilience lander. Well, that's its English name. In Japanese, it's Hakuto R. This is from a company called iSpace. You may remember in 2023 they tried to put a lander on the moon, and it fell over. So they're having another go on Thursday. We will be covering it live here on Space Oddities, starting at 7:10. Their coverage starts at 7:10 in the evening. We'll be going live just before 7, maybe 10 to 7, 5 to 7 or something Thursday evening. Hope you can join us for that live coverage. I mean, it's not every day that we see a spacecraft landing on the moon. And Daz is going to be telling us a little bit about the Resilience lander a bit later this evening, so you'll be prepared for the landing on Thursday. So we're really looking forward to that. And obviously the best of luck to iSpace for successfully putting a lander on the moon, because there have been a few failures the last couple of years. But as we always say, space is hard. If you would like to support Space Oddities, you may do so, and we would very much like you to, obviously. You can buy us a coffee. And if you just scan the QR code that's on the screen or click the link that's just appeared in the chat, that will take you to the wonderful world of Buy Me a Coffee, where you can buy us a coffee. Much appreciated. Helps us keep everything going, because we have bills to pay like every other channel has bills to pay. Nothing comes free, so we have to keep the show going. So any coffee you can buy us, that would be much appreciated. You can also click the super chat icon, the one with the $sign underneath the chat window, to make a donation directly. Or, of course, you can buy our wonderful Space Oddities merchandise at the Space Oddities shop. And again, you can scan the QR code or click the link in the chat to get your lovely Space Oddities summer t-shirts. And we also have hoodies on offer there at the same place. So go and have a look at the merchandise, get yourself kitted out for the summer, in the case of the t-shirts, and the inevitable autumn that will follow with the hoodies. And thank you for your support. They're good quality stuff, and your support is much appreciated. So what we're going to do today, we're going to go straight away over to Roger in a moment. Before we do that, I just want to mention something. I ran a poll for viewers on the Space Oddities YouTube channel, where I asked you to select from 4 options about what you would like to see more of on Space Oddities. And we didn't have that many responses, and it wasn't enough to extract any meaningful data from. The other idea we have is that we get together with some of you in a meetup here in the studio to discuss, not broadcast, not streamed, obviously, but just have a chat about what you'd like to see from the channel. But instead of doing all that, what we thought we'd do is to ask you tonight to put in the chat any feedback you have. What would you like to see more of on Space Oddities? Is there anything you'd like to see less of? Anything in particular you would like to see us cover, perhaps as a one-off or on a regular basis? So any suggestions at all for what you would like to see on the channel, please put them in the chat this evening, because we would love your feedback, because this is as much your channel as it is ours, after all. So please, if you have any ideas about what you'd like to see on Space Oddities, some things we may not have even thought about, this is your chance to put it in the chat, and you can help shape the future of the channel, because you're our wonderful audience and we want to give you what you want. So anyway.
Are there suggestions bound by the constraints of legality, or just anything goes?
Well, yeah, try and keep it within the bounds of legality, and no furry animals or drugs involved. So
that limits it.
Yeah, I'm sorry, but there we go.
Not even tribbles.
Yeah. I thought we banned the mention of anything to do with Star Trek on this.
I can remember discussing that.
You were washing your hair that week, Daz.
Oh,
So-
it was that time of year, was it?
Yeah, it was. No, we're not talking about your bath night. We're talking about your washing your hair on a regular basis. So anyway, so please take this opportunity. Tell us what you want to see on the channel, what you would, if anything, want to see less of on the channel. Any suggestions, no matter how wonderful, brilliant, terrible, awful, whatever, please put them in the chat this evening, because we rely on you, our audience, to tell us what you would like to see. If, on the other hand, you're totally happy with what you see, well, if you could just mention that as a comment as well, so we can count that as a data point. So if you're happy with what you're seeing on SpaceOddities, just say, I'm happy. So there we are. All right, then. So let's get things moving this evening by going over to Roger. And Roger, as ever, reliably is going to do the night sky and the viewers gallery this week. So there you go, Roger. Take it away.
And here we go for the first full week of June already. So, okay, so we're working our way up from first quarter tonight on the moon, and we're heading over towards the full moon roughly a week's time. How time flies. So we're currently experiencing just Mars in the night sky at the moment, but we do have the galaxies in Leo and Virgo to still study. But we are now getting to see, as the night progresses, the summer triangle. But we also have the Milky Way coming up through as well. So things are looking quite interesting. So let's see how that goes. Right, so as we get through the week, the moon will get lower and lower through the week as it does. But before sunrise, we have got quite a few planets following and preceding and following to the sunrise. We've got Saturn, Venus, and then Uranus, and then following on behind, we've got Mercury and Jupiter is coming to join up as well. So that will be interesting, although Mercury and Jupiter will be quite close to the Sun for visibility, but there might be a very careful observation to spot that if you're quite lucky, but obviously not quite just yet. But as the week progresses, you may notice that Mercury and Jupiter will have an interesting conjunction over near the last week, sort of Sunday and Monday. So might be an opportunity to get something, but obviously because it is quite close to the Sun, it might be rather difficult to achieve an image of that, but you can only try. Now, as there's been a very much lacking of comets and stuff, I thought I'd just put this up in case anyone's interested in the asteroid Vesta, which is in Virgo. So it's in a reasonable good location. It's right near the back end of Virgo. And that might be of interest to track its movements through this as we progress through the month. And it's not too dim. It's 6.3 to start with. That's through to about 6.9, so it's not too bad. So there is an opportunity to get some movement of Vesta as it moves through the constellation. Okay, so onwards with the SpaceOddities gallery for this week. We've only got a few contributors this week, but we have got an interesting gallery. And the first one is from panelist Michael, who took an iPhone 14 shot of the crescent moon on the 29th of May.
Yay!
And a very nice.
You can on the original, you can almost see the Earth shine as well.
Yes.
Right.
I don't know.
I take back everything I ever said about the iPhone. That's pretty nice.
Okay. Don't know what that black mark is. It's 2 o'clock on the moon, above the moon. But anyway.
All right.
It's a bird.
Yes.
Or is it a plane?
It's
no. Yep.
It's one of those near-Earth objects going through.
Yes, that's right. That was last Thursday.
So we've got a few from Tom McCrory, who is of the PixAstro app, He's put some interesting objects in. This one's of the Pelican Nebula with 18 hours of exposure with his Skywatcher 200p Newtonian. So he's done this in
18 hours.
Yeah, he doesn't do quick snaps. So this is a
don't these people have jobs?
yes,
Oh, sorry.
yes, he does. And this is the Pelican.
Wow.
Wow.
That
That's
looks like an oil painting, doesn't it? That's beautiful.
yeah.
Mm.
That's it's like a Matisse.
A Matisse.
All right. Matisse.
Wow, that's beautiful. Well done, Tom.
What you can do with the Pelican, or part of
That's
it. Anyway.
amazing. That's amazing. Look at the colours. Jesus.
And we've got another interesting version from Tom of the Rosette. But this is only around 8 hours. So this is quite quick for him. So also using his 8-inch Newtonian. And this is a more of a central core image of it.
Wow,
Lovely.
that's amazing.
Stunning.
That would look nice, big and framed, wouldn't it? Well done, Tom.
Good.
Great. Well done, Tom. Wow. Okay, so thirdly from Tom is the Tadpoles Nebula. And this is 16 hours. And he's used a couple of different telescopes of different focal lengths, 1,000 and 750. And the tadpoles here are 10 light years approximately in length, just to give you some scale. And this is his interpretation.
Wow.
That's the big.
That's
So much definition in these pictures.
I mean, that could be a Hubble image, couldn't it? Easily.
It could be, yeah.
Well, wait, maybe it is. That's my money. That's where I'm putting my money.
Don't be silly. It's a sea star.
S30.
So those tadpoles are 10 light years in length. So that's 60 trillion miles in length. Gosh, amazing.
Yeah, amazing. Of course, Rachel used to like doing things like that, didn't she?
Yeah, she did. Very much.
Yes. Okay, so Melot 15 from Tom, and this is 23 hours of exposure. And this was on his 533 and AM5 mount. And this was his...
Oh, man, that's the best one of all.
Oh, I like that one.
Wow.
That is definitely good.
22 hours, you can't see anything really, but 23 hours,
23
wow.
makes all the difference, yeah.
Wow.
Wow.
Yes, he's got some crackers there, hasn't he?
Wow.
Right. And then there's some from me.
Oh, here we are.
This was from last night. This is a daytime moon and a nighttime moon.
Yes, saw that last night.
Yeah.
Lovely.
Oh, they look surprisingly similar for some
Yeah.
reason.
Well done, Roger. That's beautiful.
Yeah, I did do a poll on Facebook, and most of them did like the nighttime version, but there were quite a few that liked the daytime version as well. So, you know, personal taste. But
Are these stacked images, Roger?
Yes, they are stacked, but they were done through a program called SharpCap, and there's a stacking tool in that does it immediately and then saves it as a TIFF. So you don't have to get a video file and then put it into auto stacker to make a TIFF and then process it from there. This one you can do it straight in SharpCap, and then you have a TIFF to just adjust as you want from that. So it's a lot easier. Saves a lot of space on your laptop or hard drive, whatever you're using to save the files on. So it's quite good. Right, and the last one is another one from me, and this was the sun yesterday, just showing some of the activity around the left-hand side is the eastern limb, and then on the right-hand side we got the western limb. So they are almost opposite sides of the sun.
Lovely, isn't it?
This is amazing.
Yeah.
20, 30 years ago, only professional astronomers could do anything like this. Now this technology is pretty widely available.
We have a question in the chat from Paul, who says, "Isn't stacking moon images harder than planets and nebulae since it's rotating all the time?"
No, because I stuck it and it only takes just a few minutes, so it doesn't take that much time at all.
No, absolutely, because the moon does take 28 days to rotate once, so over a few minutes you're not gonna notice anything.
Yeah.
Thanks for that, Paul.
You don't get and you don't get any field rotation in that short time if you're using an Altaz mountain either, so it's not a problem.
Yeah. Yes,
so,
indeed.
So that's what we have for this week.
Okay, thank you very much. That's great. Thank you very much again. And don't forget, viewers, if you would like to send your images in to the Space Oddities gallery, you can attach them to an email, one per email, please, and mail them to gallery@spaceoddities.space. As always, don't forget that everybody who submits an image will get it added to their own gallery on the Space Oddities website, which is https://spaceoddities.space, as I'm sure you know by now. So
yeah, they're already up there on the web.
There we are. Roger does keep
week.
the website gallery updated, so go and have a look. We've got about 200 images in that gallery on the website now. So if you want to see more of our viewers' images that we featured on the Tuesday live stream, then that's the place to look. And thank you for your support. There's all sorts of other stuff on the website as well, of course. So do go and have a look. Okay, moving on. Firstly, don't forget, if you have any feedbacks about what you would like to see on Space Oddities in the future, don't forget to put it in the chat this evening. It's your chance, as I said, to influence the way the channel goes over the next year. So please, any feedback you have at all, do put it in the chat, regardless of what it is, because we want to know, because you are our audience. Okay, let's move on. I mentioned a couple of weeks ago that there was quite an important milestone reached in the current observing run of the gravitational wave observatories, which connectively are known as LKV, and that stands for LIGO, which is the Gravitational Wave Observatory, two of them in the United States, CAGRA in Japan, and Virgo in Europe. And they do have the rather catchy acronym of LKV. So if I mention LKV in the presentation, you know what I'm talking about. So what happened in the current observing run, they reached their 200th detection of a gravitational wave event, which is a big thing considering that only a couple of years ago, the detection rate was much, much lower. So the technology is being improved all the time. So I thought what we'd do this evening is to take a look at where we've been with gravitational wave astronomy and where we're going. So just give me a second to set this up. And we will have a look at the gravitational wave, the state of gravitational wave astronomy, if you like. Hope you can all see that. So this is the update for June 2025. So we're going to start at the beginning and just go back over the timeline for those that may not know about it. And we start back in 2015 with the very first detection of gravitational waves by both LIGOs in Hanford, Washington and Livingston, Louisiana. You can see the two signals at the top there detecting the now legendary gravitational wave event. This was, in fact, the merger of two black holes that happened about 1.1 billion years ago. And the great thing about this was that LIGO actually wasn't operational at the time. It was going through an engineering run prior to going live for the first time. And almost immediately when they started this test engineering run, they received these signals. And for several months, they did their best to try and prove that they weren't gravitational waves. It took them a long time, but finally they had to come to the conclusion that, yes, these were gravitational waves, having gone to enormous lengths to disprove the fact that these are gravitational wave signals, which is what you do in science. Science is more about proving things aren't true rather than they are a lot of the time. A prediction of Einstein's general relativity a century earlier, this commenced the first observing run of LIGO, the American Laser Interferometry Gravity Wave Observatory. And the first detection in September of 2015, which was designated GW for gravitational wave 150914 after the date it happened, commenced the new science of gravitational wave astronomy. If we then move forward a year to 2016, that's when they published the results in the Physical Review letters after, as I said, trying to convince themselves that they weren't gravitational wave signals. They announced to the world that they were. And on January the 19th, 2016, the observing run 1 ended. And all they managed to detect between September and January was 3 binary black hole mergers. On November 2016, they started the second observing run. Moving forward to 2017, the main event of 2017 was the detection of the collision of 2 neutron stars in a cataclysmic explosion. You can see at the top, this was in the galaxy NGC 4993. There's an animation there showing the explosion caused by the colliding neutron stars fading. And this was a massive event for the new science of gravitational wave astronomy, because not only was radiation discovered firstly through gravitational waves, gravitational wave radiation as against electromagnetic, it was also observed shortly afterwards in gamma rays, X-rays, optical and radio waves, the radio waves being released last by the site of the explosion and arriving 13 days later. So this is what was called the first multi-messenger event, where we can now observe cataclysmic events in the cosmos through gravitational waves and then right across the electromagnetic spectrum. It's a real new era of astronomy. Observing run 2 ended in August of 2017, and the detections were binary black holes, that's black hole merger 7, and 1 merger of a black hole and a neutron star. And obviously this collision of 2 neutron stars happening just a few days actually before the observing run ended. So if the observing run had ended a little earlier, we probably wouldn't have seen this. So that was very lucky. Moving forward now to 2019, this was the detection of a mystery object, GW 190814. This was a merger between a black hole and a compact object, and we're still not sure what it was. It was either the heaviest neutron star or the lightest black hole ever found, because it had only 2.6 solar masses, and we still don't know, whether this was a heavy neutron star or an extremely light black hole. But this was the first detection of its type. Moving to 2020 was this incredible event. This was a pair of merging black holes with 85 and 66 solar masses, respectively. This gave rise to a single black hole of 142 solar masses. And if you know about black hole masses, you'll know that it was very, very heavy for a black hole, for a so-called solar mass black hole. Well, in fact, this turned out, with its incredible mass, to be the first of a population that Daz was talking about last week. In fact, these intermediate mass black holes that are between solar mass black holes and supermassive black holes. The population of these has long been surmised to exist, but here was the first concrete evidence that these intermediate mass black holes formed from the merger of 2 lighter black holes actually exist. Then we move forward to 2021. Observing run 3 ends. It was cut short by COVID, but during its time, observing run 3 detected 50 merging black holes, 2 black holes colliding with neutron stars, and 4 neutron stars, 2 binary neutron stars. This is 2 neutron star collisions and a neutron star, a black hole collision numbered 4. So you can see that as the technology goes on, and it's gradually improved all the time, the number of detections is getting more frequent and new types of objects are being observed. In 2023, observing run 4 commenced. It's broken into 4 parts from May 2023 to January 2024. Then they took a break for what they call commissioning, that is upgrading the technology. It started again in April, running to January this year. And the new observing run starts tomorrow, and it's scheduled to end in November. So tomorrow we have the start of a new observing run at LKV, LIGO, CAGRA, Virgo. And all of them have been upgraded, their sensitivity increased, and we should see a commensurate increase in the detection rate as well. Also in 2023, Black Gem became operational. Now, if you're not familiar with Black Gem, this is at the La Silla Observatory in Chile. It's 3 telescopes with 65 centimeter mirrors. Their objective is to quickly find optical counterparts in the sky for gravitational wave events. So in other words, when a gravitational wave event happens and the 3 observatories, LIGO, CAGRA, and Virgo, manage to triangulate on the sky roughly where the event happened, these telescopes will quickly, under remote control, swing to look at that part of the sky to see whether anything can be seen. Because we know from the neutron star collision in NGC 4993 that I mentioned earlier that indeed things do become or can become visible, that we saw that one right across the electromagnetic spectrum. This is what these telescopes will do. They are designed to operate autonomously. If they receive a gravitational wave alert, they will automatically swing to look at that part of the sky to see if anything can be seen. So this is a great project. There are only 3 of those telescopes at the moment, but they will be expanded up to 15 telescopes. And as well as reacting very quickly to gravitational wave events, they will also be engaged in photometry and mapping the sky. So really weird looking things in Chile, but hopefully they will be useful when it comes to finding optical counterparts for gravitational wave events in the sky. Moving to back to observing run 4, the LIGO, well, all 3 of them, LIGO, CAGRA, and Virgo were upgraded, and this should improve the detection frequency. Moving to this year, the Indian government has finally given the go-ahead to the construction of LIGO India, and I believe construction is actually starting within the next couple of weeks. So this is great news. There's going to be a LIGO in India. The more gravitational wave observatories you have, the more precisely you are able to triangulate the point of gravitational wave events on the sky. That would be useful for those 3 telescopes in Chile at La Silla to have a look at that area of sky. And as we said, in the current observing run, they've done over 200 detections. This represents 1 detection every 2 to 3 days. So a massive increase in detection rate from the original LIGO. So where are we? Well, to date, since 2015, since the start of gravitational wave astronomy, roughly 260 black hole mergers have been observed. Black hole and neutron star mergers 5, binary neutron star mergers 5, and neutron star and black hole mergers 10. So you can see the overwhelming majority of the events that have been detected are black hole mergers, meaning, of course, that this is giving us a really interesting look into black holes and their evolution and lifespan. And the fact that these are happening extremely often means that there are almost certainly a lot out there we're not observing. So, you know, we can see that mergers between black holes in the universe are really common. So there we are. Now, the recent scientific highlights have been, first of all, that scientists have successfully simulated the complete journey of a gravitational wave as it interacts with the black hole's curved space-time from the infinite past to the infinite future. This achievement offers deeper insights into the energy dynamics of such interactions. So they've managed to simulate the whole life, if you like, of a gravitational wave in the vicinity of a black hole. And that will tell us, hopefully, a lot about black holes themselves. And as it says, the energy dynamics in that extreme environment around black holes. Also, simulations indicate that collapsars, these are enormous stars rotating that are collapsing. These can emit gravitational waves detectable up to 50 million light years away. And this does open new ways of understanding the life cycle of stars. If we can detect any of these, we're not quite there with the technology yet to be able to detect these, but that will happen soon. It will give us another window through gravitational waves of understanding the life cycle of stars. And the enhanced detection technologies, new types of mirror, adaptive optics, and all sorts of lovely improvements to reduce the noise and increase the precision of these gravitational wave measurements. Now, what about the future? Well, as I said, the Indian government has finally just approved LIGO India. That will be complete by 2030. So that will join the two existing LIGOs and the Japanese KAGRA and the European Virgo gravitational wave observatories, giving us greater precision in observing these events and trying to work out where they happened on the sky. Moving to 2034, we mentioned this before, LISA, the Laser Interferometer Space Antenna from Europe. This is Europe's gravitational wave observatory in space, a triangle of satellites lagging behind the Earth in its orbit, about 1 million miles from the Earth, and using lasers fired between this triangle of satellites, and the laser beams would be millions of kilometers long, allowing us to detect gravitational waves at much lower frequencies. What sort of things are we talking about? We're talking about intermediate to supermassive black holes, and perhaps even gravitational waves from the birth of the universe. Because, as I probably mentioned before, although at the birth of the universe, light could not travel across the universe for 380,000 years because the universe was simply too hot and dense for that to happen. After that, we know about the cosmic microwave background, which was the universe's first light, if you like. But this 380,000 years after the Big Bang, gravitational waves saw no barrier to moving across the universe because they're not in the universe. They are ripples in space-time itself. So it's possible, although they're ultra low frequency, it's possible we may be able to detect gravitational waves from the Big Bang itself. And that will be stunning. What more can one say? Then moving forward again, 2035 should see the operation of Europe's Einstein telescope. Now, this is an underground gravitational wave observatory. It's been put underground to insulate it from seismic activity, vibrations happening on the surface, anything like that. And it's a massive European project. It's all going ahead. They hope to start construction of the Einstein telescope in next year, actually, 2026, should be complete by 2035 and start taking data. It's going to be built on the borders of Germany, the Netherlands, and Belgium. And they found an area with an unusual property to its soil. The soil is an amazingly good insulator against vibrations. It's the perfect place, in fact, to build a gravitational wave observatory. And it's all going ahead. Just let me show you some art concepts of what Einstein's going to look like inside. I hope one day I'd love to be able to walk down one of those tunnels. This is my kind of place. So that's what it's going to look like. This is going to be the construction underground. And if I remember rightly, the arms of this observatory, whereas the LIGO arms are 2 kilometers in length each, these are going to be 12 kilometers in length. So again, they'll be able to find gravitational wave events at much lower wavelengths, much bigger objects like supermassive black holes merging. And Europe is taking the lead in this sort of technology. But not to be outdone, America is going to build a gravitational wave observatory called Cosmic Explorer. Now, this looks to be an amazing project. It's been recommended by the NSF, the National Science Foundation, as what should come after LIGO. And whereas, as we said, LIGO has arms 2 kilometers each in length, well, Cosmic Explorer is going to have arms 40 kilometers in length. Now, they're working on what's going to work out best and what's best economically. That is to say, 2 arms 40 kilometers long, and one with a smaller one with arms 20 kilometers long, or 2 with 20-kilometer arms, or 2 with 40-kilometer arms. They haven't quite decided yet what the design's going to be. But this thing is, if it works and it gets built, it should be absolutely stunning, because what it will enable astronomers to do is, firstly, it's going to be many orders of magnitude more sensitive than LIGO. And if all goes well, it should extend the range from which we're able to detect these gravitational wave signals to the edge of the observable universe. So we'll be able to detect gravitational wave events at the edge of the observable universe if all goes well. However, of course, there's a spanner in the works here, because the National Science Foundation is facing massive budget cuts under the Trump administration. So whether this actually does get built in the end is open for question. Let's hope that it does. Could I ask somebody at this point to copy and paste the links out of the notes window into the chat for the viewers? If I could ask somebody to do that. Somebody's just going to post the 2 links. There's one link to a PDF about Cosmic Explorer, about the science case for it and everything you could possibly want to know about it. The other link is a link to the Einstein Observatory. And again, there's all sorts of useful information in those files about the Einstein Observatory if you want to do extra reading. They're both incredibly interesting. So do follow those links and download the PDFs. If you're interested in this sort of thing, they're really interesting. They would tell you all about the Einstein and the Cosmic.
Yeah, just posted those, I think.
Thank you. So from 2035, this is what the world will look like in terms of gravitational wave observatories. In the US, we've got the 2 original LIGOs plus Cosmic Explorer coming along a bit later. We've also got Advanced LIGO Plus, which is one which may be built in South America. It's being thought about at the moment. The Einstein telescope in Europe, and the Virgo telescope, or observatory if you like, in Europe. Then we've got LIGO in India. We've got CAGRA in Japan, and another project which the US would like Australia to cooperate with. At the same time they're building Cosmic Explorer, is a sort of Cosmic Explorer South in Australia, which has got the codename Nemo at the moment. So just, basically to cover all the latitudes across the world with these gravitational wave observatories, to enable the ultra precise precision detecting these objects on the sky, so that we can see exactly what's going on at that point in the sky. And of course, all of these observatories will work together. They will complement each other and just work as a complete suite, if you like, of gravitational wave observatories. So exciting times ahead for gravitational wave science. Now, the gains that we hope to get from all of this, firstly, mapping the population of compact objects like black holes and neutron stars, finding out, how many there are out there, how do they evolve, if do they evolve on their own, what happens when they're in pairs, how do they evolve then. So we're going to learn a lot about the populations of neutron stars and black holes. Also, one scientific goal is to understand what the hell is inside a neutron star, because we really don't know. There have been all sorts of ideas about what is inside a neutron star. We're pretty sure that there's some pretty wild, exotic matter inside neutron stars. And everybody's, there have been suggestions ranging from quarks to bosons to all sorts of exotic material that perhaps we've never heard of. But with gravitational waves, we should be able to work out exactly what's inside neutron stars. Refining the Hubble constant, well, we talked about this earlier, the expansion rate of the universe. Testing general relativity in extreme conditions. If you want to test a scientific theory, what you do, of course, is you test it in extreme conditions to see if it breaks. And that's what we want to do with relativity. Of course, we all know that relativity so far has passed with flying colors every single test that has ever been thrown at it, and there have been countless tests thrown at it. But, you can never say never. So testing relativity even further is another scientific goal. Discovering this elusive population of intermediate mass black holes that we think are out there, but we've had very few candidates for so far. Constraining dark matter models. Gravitational wave astronomy should tell us a lot about whether we've got the models of dark matter correct or not. Multi-messenger astronomy, as I mentioned earlier, and astrophysics, these events that are detected in gravitational waves and then right across the electromagnetic spectrum, complementing each other and building up, complete pictures of the event across the EM spectrum, and observing supermassive black hole mergers, which would be particularly interesting because there's a lot about supermassive black holes that we still don't understand. And to be able to watch them merging. Although, of course, there's the final parsec problem. There's this idea that, in fact, even supermassive black holes lack the momentum to come within 1 parsec of each other because their gravitational waves prevent them from doing so, because it weakens their trajectories, if you like, and stops them getting closer than about a parsec. So there's this idea that supermassive black holes don't merge at all, but we'll find out hopefully through gravitational wave astronomy. And there you have it. That's the gravitational wave update for this month. I hope you found that interesting. And there's a lot going on, and you have to say in just 10 years this science has come along out of all recognition. It's a really exciting time now that we are no longer confined to observing the universe purely through light, but through, if you like, the structure of the universe itself. Then who knows what we're going to discover. It's really, really exciting stuff. Okay, there we are. So guys, got any comments about that?
Oh, it just seems so amazing that it was only 5 minutes ago that we're actually reading about these theoretical waves that travel through space and time. Everything's moved so fast, it's very, very, very fast moving, and it's very exciting. It's an exciting area of.
Yeah, and Paul says, in fact, thanks, Andy. I'd wondered how they could find a tiny, precise point in space where the wave originated. The amount of information we're learning from this new science is really exciting. I agree with you, Paul. Absolutely thrilling. It's just amazing. And of course, don't forget, you can all make your own gravitational waves. It's very easy to make gravitational waves because any object in the universe that has mass and is accelerating generates gravitational waves. So as I get people to do when I lecture on this stuff, is if you just put your arms in the air like this and then accelerate them like this and get faster, you have just generated gravitational waves that will be traveling across the universe at the speed of light long, long, long after you're dead. Einstein believed that gravitational waves never die out entirely. They get weaker and weaker, but they never die altogether. We now believe there may be quantum effects that will, in fact, kill the gravitational waves eventually, but they do last a hell of a long time, up to billions of years. So just think of this. Long after you're dead, every time you've moved, you've accelerated, you've written that gravitational wave into the universe. It will be traveling across the universe at the speed of light in perhaps a billion years or maybe even longer. So you've written part of yourself into the universe for the next billion years. And I think that's a really romantic thought. So think about that one.
Andy, we were talking about potential setbacks from funding problems. I remember 25 years ago or so, I used to run a series of science data center symposia. And we had a woman speak on LISA.
Oh, yes.
Which was planned to be built much earlier, and how we would store the data and what we would do with it. But it has been that long since the first the first formal organized plans for LISA. So it's nice to see this coming about.
And don't forget, we've already had the LISA Pathfinder, which was launched several years ago now to test the technology, and it outperformed everybody's wildest expectations. So the mission scientists were absolutely thrilled that LISA will work, because they tested the technology in space already. So it's just a question now of building it and getting it up there. But it does. This is how long these projects take. And when you think that LIGO was being talked about back in the 70s, everybody thought that they were mad. People like Kip Thorne were talking about something resembling LIGO, and everybody said no. Gravitational waves don't exist, or well, they do exist, because Einstein thought that they exist, but they were too weak to be detected with any technology that we could put together. But he was wrong. I mean, Einstein spent 20 years prevaricating about whether gravitational waves exist or not. And, he just flipped between, no, they don't exist. Yes, they do exist. But he couldn't ignore that they were in his maths and that they popped out of the math of general relativity. And in the end, he convinced himself that they existed, but he thought, we'll never find them. They're too small, too weak to be detected by technology. And he was wrong. So there we are. Did those links end up in the chat then? If not, let me just have a look.
I can see them.
No, don't see them. Okay, just give me a second.
I did put them in there.
Put those links. Oh,
Unless
God, I don't know. Okay, just give me a second. I'll just put them in the chat now.
Yeah, they are there.
There we are. There are the two. There are the two links to PDFs about the Cosmic Explorer and about the Einstein project. Oh, right. They're twice now. Right.
I know they're there, yeah, but they weren't
okay.
before. Yeah, that's okay. That's fine as long as they're there.
Right. Yeah. So anyway, so that's the state with gravitational waves. Obviously, I'll keep you updated on the state of play, because this science is just revealing new things all the time. And don't forget, LIGO will start a new observing run tomorrow, along with CAGRA and Virgo. They'll be working together. So who knows what we're going to find after a brief pause for an upgrade. So there. All right then. So where do we go from here? Well, what we're going to do now, we're going to go over to Roger, who's going to give us his 3 things.
Ooh. Right.
Roger, as you may recall, was not able to
What could that mean?
participate in the 3 things last week because of miming problems. So which one do we do first, Roger?
Just pick a card.
Okay, pick a card. There we are. There we are.
Right.
The largest known galaxies found so far away.
Yeah.
Yeah.
Okay. Right. So here we are. We're trying to find out what we have so far seen in the universe, and we have been fortunate to see these 3 huge objects Now our Milky Way is roughly 100,000 light years across, and these are in the order of 17 times and about nearly 15 times larger in diameter. So things are rather on the bigger scale here. So not only are they in 1.7 million light years in diameter, the smallest, narrowest part is also quite considerably larger as well. So it's been quite fascinating just to see how large some of these objects are. Absolutely huge. Hopefully I've got some images to show you of these objects. This is the largest one, which is in Centaurus in the southern hemisphere. And these are obviously from the Hubble telescope. And roughly I don't expect anyone would be able to actually image them. But obviously from the image that you can see on the left there, all the thousands of other galaxies that are also included in the photograph as well. So it's quite an interesting thing to see.
It makes you wonder how galaxies can possibly grow that big. I mean, it's just
obviously there might have been a few mergers to make them this big, I'm sure.
Yeah, absolutely.
This also goes back to it all comes together, right? This all goes back to the Hubble constant. If you're looking at the cosmic microwave background and the clumpiness of dark matter in the early universe, some places were pretty clumpy with it, if there is dark matter, and some places weren't. So perhaps these are galaxies that formed around very large clumps of dark matter.
Yeah. Oh, can I have that in writing, Lou?
Well, sure.
Now here's the second one, which is only slightly smaller, but this one's in the Radinus, which was also only visible from the southern skies. But looking at the picture there, it almost seems semi-transparent on this image. So should be an interesting way of measuring that. I don't know how they've managed to, but there's some rather fascinating galaxies there. It looks like just through the top part there, you've almost got like the Siamese galaxies where they're sort of interactively joining together there. So lots of fascinating galaxies in that region as well, from our viewpoint.
Yeah.
And then we've got the smallest one of the three, which is only 1.45 million light years in diameter, and this is in Sculptor. They're all in the southern horizon, in the southern atmosphere, southern sky. So unfortunately, none of us would be able to capture it, not even with the little sea star. But there we are. But it just goes give you a scale of how many times these galaxies are compared to our little Milky Way. A mere 100,000 in diameter. Okay, so that concludes the three largest known currently observed galaxies. We will then go on to another one.
Okay, so this is
stars.
And similarly, the largest known stars.
I'm going for size here.
Oh, I bet you are.
Yes. Hang on. Where is it? Hang on.
Have you lost your stars?
I've only got this one, which is one I've just presented, and the other one, which is. Have you deleted it?
Oh, okay, right. Let's move on to the next one then.
We've also got the James Webb.
Okay.
And we've got some here that we have from when we first initially started it 3 years ago. So
okay.
Right. So how come you've got it and I haven't? Oh, there we are. Right. Okay. So these are just the ones from my personal selection. But these were all from 3 years ago when the James Webb was starting to go in fully operational. And this is obviously everyone's one of their favorites. So the Pillars of Creation, in the Eagle Nebula, for these images to be seen. Absolutely fascinating, especially when you can sort of see everything that's behind the nebula, which the poor old Hubble couldn't actually see because it didn't have the facilities to see through it.
Yeah. Beautiful.
Now, Derek's put a question in saying, will larger galaxies have larger black holes? Well, it depends on how they were originally formed, I guess. If it was obviously merging galaxies, then obviously they might have collided together to be able to make a bigger black hole. But we may find out at some point.
There is a direct linear relationship between the size of a supermassive black hole at the center of a galaxy and the size of the galactic bulge, which is that mass of stars in the middle of the galaxy. There's a relationship between the size of those. It's very clear. It's linear. We don't know what it means. So as far as the galactic bulge goes, the bigger the black hole, the bigger the bulge. In other words, it's more a relationship between their mass than the actual size. But we don't know what that means. It's a bit of a mystery. But yes, as Roger said, if galaxies have been built up from mergers with other galaxies, then if those galaxies had supermassive black holes, they would tend to sink towards the middle of the galaxy, and the two black holes would co-orbit and perhaps eventually merge over a very long time period.
Yes.
But we don't know, really. We don't know. This is all a bit up in the air, as it were.
Yes. And they are quite a long distance away, so it does make it a bit more difficult to be able to do the calculations and the measurements to be able to guess what actually happened. Yeah. Okay, so that's the Pillars of Creation. And then we go on to the Carina Nebula, which was another fantastic image. In fact, this is one of the first ones that they did actually produce, didn't they? With great fanfare. Unfortunately for us, the Carina Nebula is down in the southern hemisphere, so we aren't able to do it unless Kenneth Holmedal decides to use one of the remote telescopes to image it. I'll suggest it next time I have a chat with him. Yes, another fantastic image. The way that it's all been picked out detail-wise is absolutely amazing.
Yeah, it is.
Then my third choice is this: the protostar in Taurus. And the estimates of this, that the star is only 100,000 years old by the calculations.
Yeah.
So it's only just sort of in a blink of an eye just started to form, and this is the results of that initial creation period. Some fantastic details of the gases being forced away from the star there. Amazing.
Beautiful image, isn't it? Absolutely.
Well, those were my three selections from 2022, the first year of its full year of operation from the James Webb Space Telescope.
Right. Thank you very much, Roger. That's fantastic.
Right.
Okay. So anyway, we finally got you done, as it were. Going to move over to Lou now, who's going to be telling us about the exploration of Jupiter. But before he does that, we have a bit of a sad death to announce in the astronomical community. Very sad this week, but Lou's going to tell you about that, I hope.
Let's see here. Let me share my screen.
Yeah.
That and that.
Okay.
Ooh.
Now I do this, and I'll go to full screen mode, and it will have problems. But let's see if we can do it right this time. Slideshow from beginning. Well, do you see the title slide?
Not as a slideshow, no.
Okay, I knew it. I knew it. Well, we will run it like this then.
Okay.
Okay. Well, I'm afraid that I did not follow directions. I did not follow directions today. Andy asked me to look at a comparison of two spacecraft heading to Jupiter as we speak. Thought, well, I'll just expand that a little. We'll talk about discovery and exploration of the Jovian system. Said, oh, that's too big. That'll take too long. We'll just make it of Jupiter. Oh, that's even too big. I'll just do pictures of Jupiter. Well, that'll be too much. Well, just spacecraft images of Jupiter from space. So we are going to talk about that.
Sorry, can I just ask, what happens if you click the slideshow icon at the bottom of the screen there?
Let's see. This one here?
It's right at the bottom, next to the slider on the bottom right-hand side. Looks like a little screen motif.
Yeah, it's not on my...
we can see it.
You can see it. That's...
No, go left, left.
That's it.
Left, stop, click.
Oh, this one. Oh, well, let's find out.
No.
Oh, well, that was worth a try.
Yep. We'll figure it out later. So, but as Andy said before we get started, some very sad news in the field of astronomy and in the field of astronomy outreach. Dr. Fred Espenek passed away 2 days ago on June 1st. He was a remarkable scientist, as well as doing worldwide outreach. And most of you know Fred for the work that he did with eclipses. I'm not sure Fred ever missed an eclipse from the time that he first had to travel to one. I believe he saw over 40 solar eclipses. He dubbed himself Mr. Eclipse, which was a well-earned title, wrote a number of books on timings and physical properties of eclipses, both solar and lunar, doing the math and making the predictions far in the past and far in the future. And he went to these and shared his love, his joy, his excitement of eclipses with the world. The work that he did in science outreach was phenomenal. And I worked with Fred for many years at NASA Goddard Space Flight Center. He also was an infrared planetary scientist. He helped, I guess he worked with Ted Kostyuk at Goddard to build an infrared spectrometer that they took first to Kitt Peak to look at the outer planets, and then and also to Mauna Kea, where they put it on the back end of the infrared telescope facility. And they co-authored a number of papers on the winds of Titan, the ethane in Jupiter's atmosphere, ozone on Mars, hydrocarbons in the outer planets. And eventually, Fred retired from Goddard and moved out to Portal, Arizona, where there is Arizona Sky Village, with his wife, Pat, who was also his forever observing companion. She traveled everywhere with him in the world. Amateur astronomy is certainly missing a dear friend right now, and we are going to make sure that Fred's legacy is honored at this year's Astrofest, which is the annual meeting of the Astronomical League, which is in Bryce Canyon, Utah this year, last part of June, and I will be there saying some good words as well. So just wanted to let our viewers know and make sure that we took a few moments to honor Fred and his many contributions to science and science outreach.
Thanks, Lou.
Yeah. So let's talk about Jupiter. This apparently is the very first ground-based photograph of the planet Jupiter. It was taken in 1879 by an Irish astronomer, Agnes Mary Clerk. And she published this image in a book called A Popular History of Astronomy during the 19th century. And of course, for us, it looks rather amateurish, but this was a big deal because it was the first image of the planet Jupiter. Moving on, this is an image of Jupiter that was taken with a Lick Observatory in 1891. A little bit better, a little more structure. You can see more of the Hadley cell circulation, the belts and zones in Jupiter's atmosphere. And of course, this is an image I took. I have noticed something. We get lots and lots of great, beautiful, amazing astro images, but we haven't generally gotten lots of planetary astro images, which I have always found a little odd. And of course, Jupiter and Saturn are not easily visible now, although Venus is, I guess. Anyhow, we can do better. This is an image. This is actually an amateur astronomer took this image. This is from Andrew Quone. This is all ground-based imaging right now. I just want to give a sense for where we started. He took this image on November 20th from his backyard observatory in Ontario, Canada. He used a Celestron C11 telescope, so nothing remarkable. Used a ZWO ASI 120 millimeter monochrome camera and took pictures in, I think 4,000 pictures in red and green frames, and a few thousand in blue to put this image together. So this is what you can do as an amateur astronomer. I mean, it's remarkable, absolutely remarkable. And finally, this is the highest resolution ground-based image of Jupiter that has been taken to date. This was captured by the Gemini North Telescope on Mauna Kea in Hawaii. This image uses something called lucky imaging. Do you know about this? This is a technique that where you capture many shots, many exposures, and then you select only the sharpest ones to add together to create the detailed view. And again, this technology is very available, quite available to amateur astronomers as well. The resolution here, I think, is something on the order of 0.13 arc seconds. And so the detail in this image should reveal features as small as 300 miles or 500 kilometers across. Just a stunning image. Well, that's all from the ground, but we have a rich history of sending spacecraft into space, both orbiting the Earth and 2 other planets, to observe and get other data from their proximity. So here we are. This is Pioneer 10, launched on December 4th, 1973. It was the first spacecraft ever to travel to Jupiter. It was a flyby mission, of course, and was able to make a close approach, actually behind Jupiter from our vantage point. It has this really interesting image here. This is probably one of the best images that it took of Jupiter. Immediately, you can see far more detail than in ground-based images. You can see some of the swirls. You can see much more structure in the atmosphere. So this was an achievement that talked a lot about the structure and dynamics of the Jovian atmosphere. It also took this interesting set of sequences of the crescent Jupiter. These images are not that hot, as I would say. But think about it. When we view Jupiter from Earth, we don't see it as a crescent, right? So these are the first images where you could actually see Jupiter as a crescent. So that was Pioneer 10, and its mission was to fly by Jupiter. This is from Pioneer 11. Pioneer 11's mission was to go to Saturn, but it got a gravity assist near Jupiter. This image was taken at about 760,000 kilometers from the cloud tops. And it's probably the best image of Jupiter that Pioneer 11 was able to take. So that's the Pioneer series. And from there, we go on to Voyager, of course. The Voyager spacecraft 1 and 2 launched in 1977 with 3 color images on them. And we were able to do this. This is the incoming film sequence showing the rotation of the Great Red Spot, anticyclonic vortex, right? As well as the shear in the movements of the belts and zones across each other. Just very, very dramatic. This image is a color image where they took into account the reorientation of the scan platform on Jupiter, and they made it into this beautiful animation that I'll play for you here. This is also from Voyager. Oops, let's try again.
Wow.
Really is.
So just a series of images stitched together very nicely. And you saw one of the moons going behind Jupiter there.
Beautiful, isn't it?
Certainly is. Shame he couldn't keep his phone still. That's beautiful.
Mm-hmm. See the shadow of one of the moons and another on the cloud tops. Okay, we'll stop that. And move on. This is a 3-color image up close of the Great Red Spot, taken in January 1979 as Voyager 1 zoomed past the closest approach to Jupiter. This is a close-up of not just the red spot, but all of the dynamics of the condensates in the atmosphere around the red spot that give the atmosphere its structure, features of the planet. And we're still exploring the dynamics of the Jovian atmosphere today. So that was Voyager. Now, on to Galileo. Here's an image of the Galileo spacecraft. It was launched from the space shuttle. It had a probe that was released into the atmosphere of Jupiter, as we see here in the middle image. And of course, down in the bottom was its launch. Now, you can notice that the main antenna is not fully unfurled here. And that's really what happened. They made it like an umbrella, and it didn't open entirely. So they had to do some really neat tricks at the ground station, the ground receiving stations, the Deep Sky Network, as well as with the spacecraft to condense the data they were sending and allow it to provide useful science information. And it certainly did. This is probably the best full disk image of Jupiter from Galileo. Just a gorgeous, gorgeous picture. Again, this was a 3-color camera. This is an image that was taken in 727 nanometer near IR light, which gets moderately absorbed by atmospheric methane. So this mosaic of the surface features, well, the atmospheric features of Jupiter shows a visible cloud deck in the upper tropospheric haze with higher features enhanced in bright areas over the lower dark areas. The oval cloud systems of this type that we're seeing here are often associated with very chaotic cyclonic systems. And you can see one of them here as this kind of balloon-shaped feature between two of the ovals. This is a sequence of 4 images taken by the Galileo spacecraft several seconds apart, showing the impact of one of the comet Shoemaker-Levy 9 fragments on Jupiter's night side. Just remarkable. This here, here, and here.
And that impact exploded with the force of thousands of atomic bombs.
It did. And ground-based observatories, as well as every spacecraft they could get their hands on, were looking at Jupiter during this time. Here we can see the impacts on the night side in the infrared, because of course they generated a lot of friction, a lot of heat. But of course those images were also visible in visible wavelengths. So I remember gazing at this through my telescope in West Virginia under some fairly dark skies, and my eye was just glued to the telescope. How could you not? And then I took my eye away from the eyepiece for a moment. And I noticed it was overcast. I was actually seeing through Earth's clouds.
Wow! Cool. And those impacts left scars in the atmosphere, dark scars in the atmosphere that persisted for weeks.
Yes, perhaps something like the Great Red Spot. We don't know, but there are other examples of constrained, limited features in the atmosphere of Jupiter.
Yeah.
So on to Cassini, launched in 1977. Cassini, once again, here's a spacecraft dedicated to orbiting the Saturnian system. Didn't have anything to do with Jupiter. However, it did go by Jupiter on its way to Saturn to get a gravity assist. So you use less fuel, it doesn't cost as much. And during that flyby of Jupiter, it took some amazing images. Look at this. I want to say too, I was on the Cassini ground system design team, whose charge it was to save money. And I was the only scientist on this team. Everybody else was a computer technician or an engineer, and of course, people with administrative backgrounds. They wanted to shut off Cassini after Earth orbit and then not turn it on until Saturn. And I said, no, you can't do that. So there's a lot of discussion, and good thing they kept it open. Not only did it take these beautiful images of Jupiter as it passed by, But we also had Galileo taking images and other data of Jupiter at the same time. And so it was the first time that two spacecraft were in the same vicinity, taking images and other data of the same planet. And that returned a lot of really useful information. Here's another picture of Io against the cloud tops of Jupiter, taken by the Cassini spacecraft.
That's one of my favorite Cassini images. It's just
cool,
unbelievable.
There's an animation out there somewhere with Io and I think another moon kind of slowly.
That's right. Where they one overtakes the other. It's I can't remember which one it was, but yeah, amazing images, amazing.
Mm-hmm. All right, so that's Cassini. It's on its way to Saturn, and then there's Juno. The Juno spacecraft entered orbit around Jupiter on July 4th. How did they do that? On Independence Day, right? 2016. It was the first spacecraft to peer below the planet's dense clouds to answer questions about the gas giant itself and its origins, the solar system. And this spacecraft is now in its extended mission phase. And we will see if that funding continues. It was a 5-year journey to get to Jupiter. And it's testing out some new propulsion mechanisms here. I believe that's ion propulsion.
Yes, it is. It is. It's ion propulsion. And the other thing about it was that they had a problem with it. When they arrived at Jupiter, the propulsion system had a sticky valve. So they weren't able to orbit Jupiter as often as they liked. But they did some brilliant maths, and they worked out that if they put it into a 29-day orbit around Jupiter, they could get about 85% of the science that they wanted to. So that's what they did. So it's done a lot of approaches now to Jupiter. I can't remember how many, but it's revealed some really interesting things about the core of Jupiter, which is a lot more diffuse than we thought it was. We always thought that Jupiter had a core maybe about the size of the Earth that was rocky, but it turns out to be more granular than that. And I don't think planetary scientists still know exactly what that means.
We don't. Jupiter is the largest planet we have to work with. A gaseous planet. Its density is quite low, but physically it's large. So that's still being investigated.
Yeah.
And as you say, it was able to return some very nice science data. Here we are. Here we have a beautiful full disk image of Jupiter taken by the Juno spacecraft.
Beautiful. And
so
it looks so different close up to how we see it from the Earth. It could be a different planet. It's amazing.
I think there is some image enhancement in this picture.
Yeah, probably.
So it's a little hard to know if this is what you would see if you were actually in a spacecraft near Jupiter, but nevertheless, absolutely gorgeous image. Well, that's great. So there's Juno. Seems like there are an awful lot of spacecraft that took pictures of Jupiter that weren't intended to. This is Jupiter and the Earth taken from the Mars Global Surveyor spacecraft. It wasn't even going out to Jupiter. This was taken on May 8th, 2003 with the Mars Orbiter camera, the MOC. And there was just a fortuitous planetary conjunction that put Earth and Jupiter close enough together to get this picture while it was in orbit around Mars. So there you are. Well, this spacecraft needs no introduction. This is the Hubble Space Telescope, which was able to take many planetary images, including Jupiter, not only in visible wavelengths, but in ultraviolet wavelengths. And that's important for this image here. This is actually two images of Jupiter merged together. The large reddish image was taken in visible wavelengths. And so you can see the condensates and the stratus clouds in the zones, and the condensates deeper down in the belts, and lots of great dynamical structure. But you also see on the North Pole a bluish illuminated, I don't know what to call it, but it is an aurora. It is an aurora, and the same physics applies to aurora on Earth, but they're different processes. And this aurora is there because of the material that is being sloughed off by Io from its volcanoes that winds its way along Jupiter's magnetic field lines into the atmosphere of Jupiter, colliding with hydrogen. And so this is glowing in the ultraviolet, and you need to have ultraviolet sensors to see it. Every one of the outer planets. And in fact, I believe it's the case that we have seen aurora on every planet, even Mercury. I'll check that, but certainly every one of the outer planets. So that's Hubble. And what would you imagine comes after Hubble?
Does it begin with W?
Yeah.
Of course, the James Webb Space Telescope. Different mission, different science objectives, different wavelength region. This is an infrared telescope, so it sees in the infrared, and those signals are converted into visible light so that we can see it. So here's Jupiter in the infrared, and you can see all kinds of interesting structure here, which we have labeled in this next image here. There we go. So you can see some glow from the northern and southern lights on Jupiter. You can see rings, the rings around Jupiter. We didn't know Jupiter had rings until Voyager 1 discovered them. They are so tenuous, so dark, so dusty. But here we see them because they are absorbing sunlight as well as reflected light from Jupiter and re-emitting that in the infrared, where you can see it in this image. You see diffraction spikes from the bright southern aurora here, and some of the moons of Jupiter. So just a remarkable, remarkable image. So that's it for the current spacecraft. But there are, as Yoda said, there is another. In fact, there are two others, and we're going to be talking about them next week in the Battle of the Jukebots. Will it be Europa Clipper or Jupiter Icy Moon Explorer? You decide who will win.
In the
next one, we will talk about each. We will present each spacecraft to you with all of its frailties and successes and possibilities, and you, the audience, will decide which one is the winner of the Battle of the Jukebots.
Absolutely.
Oh, it's a shame I'm not here.
Yeah, indeed. So thank you, Lou. So I mean, absolutely unbelievable images there, and you know, it's difficult to remember that this is all, you know, in terms of exploration of the universe, all very new, you know, and you know, when New Horizons flew past Pluto in 2015, that concluded humans' first reconnaissance of the solar system, and we hope that that's going to continue with better spacecraft, giving us more data, more interesting information about the planets. But that initial reconnaissance of the solar system took almost exactly 50 years, from Mariner at Mars in 1965 to New Horizons at Pluto in 2015. So yes, and you know, in terms of history, that's no time at all.
I know that Alan Stern, the principal investigator for New Horizons, was really, really hoping that Pluto would be let back into the solar system as a full-fledged planet so that he could say that he completed the view of investigation of all the planets. But so far that has not happened.
And I don't think it will either. But we will see. We will see. Stranger things happen at sea, as they say. That's why I never went to sea, incidentally, because strange things happen there apparently all the time. But there we are. So thank you, Lou. Great presentation. Thanks very much indeed. What we're going to do now, first, before we get on to resilience, just want to say, don't forget, please, if you have any feedback about what you would like to see on the channel in the future, please put it in the chat before we close for tonight. I see we've had a few comments already. Thank you very much for them. We will have a look at them and digest them later. And thank you so much for telling us what you think, because we want you to help shape the future of this YouTube channel and give you what you want. So if you have any recommendations, ideas, anything at all, please put them in the chat before we finish this evening.
Perhaps you'd like to see us all wear funny hats. Maybe that's your deal. I don't know. Whatever it is.
Or just you, Lou. I think that would be.
It could be just me wearing funny hats, and I will do it. I would do it. I would.
If you'd like to see Lou wearing a funny hat on a regular basis on the Tuesday live stream, you can put that in the chat. And if you want to specify what type of silly hat you want him to wear, please do. Make it as silly as you like. We don't care.
I have to think this one over again. I'm not sure. All right. No, I'm committed now.
There we are. He should be. So there we are. Okay. Paul says, I love all of the wonderful pictures, but it scrambles my brain to try and imagine the sheer scale of what I'm looking at. Yeah, it's our poor simian brains are not equipped well to deal with these sizes and distances and everything. But we do what we can, Paul. We do what we can, and we just have to look at the numbers and accept them rather than try and work out exactly what they mean, because you can't. Our brains aren't up for it. Don't forget, I mean, it was only in the 19th century, most people would rarely come into contact with numbers bigger than 1,000, your average person. And we're now having to deal with trillions and billions and light years and parsecs and all the rest of it, and we just go duh, because we're human and our brains just have no way of computing that. And we can compute it, but computing it in a meaningful way that we can actually grasp the concept and understand it is pretty much impossible. Yep. So there we are. Now Daz is now going to tell us about the important event of the week, which is the landing of the Japanese lander Resilience on the surface of the moon, happening this Thursday evening. We will be starting our live coverage about 10 to 7, 5 to 7, something like that, on the YouTube channel, UK time, that is, in the evening. So we hope you can join us for the live coverage, because seeing something attempt to land on the moon is always a bit of a nail biter. And there we are. So do join us on Thursday evening at just before 7 UK time, when we'll hopefully witness the successful landing of the Japanese Resilience on the moon. So Daz.
Right, as we know, this is the Hakuto R Mission 2, also known as Resilience. Now, this was a very short presentation, because really we only sort of like heard of this about 15 minutes before the show started. And well, a bit longer than that, actually. So it's only a short presentation. And the reason is that, this, if you remember, we saw this and we actually covered the launch back in on the 15th of January 2025. And it was part of a ride share with the Blue Ghost lander, if you remember. Now, the Blue Ghost lander took a direct route using engines and things like that. And in the meantime, the Resilience took the long route. It used sort of like a very elliptic orbit to actually get work its way slowly towards the moon and go into orbit. In fact, it went out as far as Lagrange point 2, over 1 million miles away. And of course, that's where James Webb is. But yeah, it's been all the way out far. It's come all the way back in now, and it's actually going into orbit. And as we heard, it's actually landing. Now, for Japan, it's the 6th of June, but for us, it'll be the 5th of June because of the time difference and all that. And it's actually landing at Mare Frigoris. Isn't that the Ocean of Gold or something like that? Is it some? Oh, I don't know. Maybe I'm getting that wrong. But that's where it's landing. It's landing on the facing side of Earth because they want to have direct contact with the machine itself. So what's actually this machine actually going to do? As I said, they've nicknamed it Resilience. It basically this is the second of 3 landers, and all the landers are based on exactly the same design. There's very little design, changes between them at all. Basically, it's using the same overall design with upgrades for each flight. As I said, it launched on a Falcon 9 from the Kennedy Space Center shortly before. It actually left. It launched on what was it? A Falcon 9. Sorry, I got myself all tongue-tied there. And it was launched from the Falcon 9 actually before the Blue Ghost was actually released into space. And as I said, the Blue Ghost took a direct route with Resilience going off into the wilds and all that to work its way back. Right, here we go. Now, the Resilience actually carries a memory disk developed by UNESCO organization, which contains 275 languages and other cultural artifacts. Well, we know all about these sort of things because the Voyagers are carrying gold discs. So, it's exactly the same sort of thing, but these are going to be positioned on the moon for later generations to pick up, or maybe, little green men. Won't say too much about them. Marvin the Martians. So, and I'm doing the same as I usually do. So this is the actual path that, as you can see, that it actually took. It launched from Earth. It actually orbited with Earth. Then it left Earth's orbit. It was then actually ejected from the rocket. It was released, and it went on its merry way. It just floated up. It passed out far beyond the moon's orbit, and now gravity is slowly pulling it back, and it will be or coming into the moon for its landing on the 5th, for us, the 5th of June. So I've got to keep reminding myself that it's the 5th of June, not the 6th of June. Basically, I said it's landing at Mare Frigoris. Let's see if we got the picture. There it is. You can see Mare Frigoris. I don't think you can see my cursor, but if you look, there's a dark strip, and you can see it's actually labeled Mare Frigoris, that goes from the left-hand side just above the center, and it comes down a slight diagonal towards the right-hand corner, and you can see there's another label. It's the thing. It stops just below that. You can see on the right-hand side a crater called Hercules, and it stretches all along there. This is where it's actually going to be landed, and as I said, this is on the Earth-facing side of the moon, so they can have direct contact with it. But there is also, just in case that there is any sort of drama, they have also got contingency plans for other landing sites. But at the moment, everything's gone for Mare Frigoris. The Resilience is actually carrying a little rover, which is called Tenacious. It's designed and manufactured in Luxembourg, so this is a European rover, and will explore the area around the landing site after being lowered to the lunar surface from the lander. So there will be, so it will have a little lander that will trud off and do its own thing. So I have got a picture of that somewhere. Now this is a full-size model of the Harka-2 brand and the rover. You can see the rover down in the bottom left-hand corner there. So it's a fairly biggish machine actually. But the little rover, it weighs literally 11 pound or 5 kilograms. So it's not that very heavy at all. So
can I just say, Daz, you were right. Mare Frigoris does mean sea of cold.
Cold.
Cold, yes, as in not hot.
Oh, okay. I actually said gold.
Close enough.
Yeah, we just got the first letter wrong. Okay, then. So yeah, well, Frigoris, yeah, of course it would be, yeah, frigid. So yeah. So there we go. So this is the little lander. Now it's actually carrying on it a model. It's carrying what they're calling the Moon House. It's a Falou red miniature cottage artwork designed by Mikhail Jenberg. The Moon House will be deposited from Tenacious onto the surface of the moon. So it's basically they're depositing an artwork onto the actual surface itself. So as I said, basically we're looking at the 5th of June, whereas the Japanese are advertising the 6th of June. But of course, that's all down to basically the time difference and all that. So basically, I hope you can join us on Thursday. We're looking forward to this. It's nice for them, as Andy said earlier on, for them not to land it in the middle of the night. So hopefully you'll be there with us. So that's it. This is a little lander. It's going to hopefully make history, and it's going to because the Japanese have been quite good at landers. What was the one, Andy? Can you remember the one that lasted for a lot longer? They thought it was only going to last one night, and it lasted about 6 or 7 lunar nights.
Which one was that? Oh God, I can't remember. Can't remember that.
Yeah, it was one. Unfortunately, it landed on its side, but they thought they weren't going to. It did do science. And they thought, well, once the sun goes down, because I think it was in the southern hemisphere.
But this
thought,
was the predecessor of this rover, wasn't it?
Yeah, I'm trying to think what it was called anyway. Yeah. But yeah, it lasted. It kept coming back to life after every night time and all that, and it lasted for several or maybe more nights. Of course, the lunar night on the moon is a lot longer than it lasts weeks. So yeah. Okay then. So hopefully you'll be with us on Thursday.
Right.
So hope to see you then. Cheers.
Hope to see you. As I said, we'll go live just before 7 p.m. UK time on Thursday, and let's hope that this lunar lander can get down on the surface, deploy the rover, and that it has a fruitful scientific venture on the moon. Okay, what we're going to do now, it's come to that time. We're going to put on our lights, our helmets with lights on, and go down the thick ropes, spelunking into the nether regions of the internet to have a look about what people have been saying on social media. Now, this week, it's a solar special because there was quite a lot of solar activity last weekend that's been in the news. And of course, if something is in the news, then you can guarantee that somebody somewhere is going to be saying something stupid about it. And so this is what we collect for your delectation and delight, dear viewers. So what I will do now, just give me 1 second. We will have a look at this week's offering in Einstein of the Week, our regular feature about what people are saying on the internet. And okay, so let's go with the Einstein of the Week solar special. Here we go. I've got 8 for you today. So the first one, and these are all about the sun and solar activity. So the first one, somebody not really understanding much, asking the question, what in the heck would cause an 11-year cycle on the sun? So again, somebody who doesn't really know a lot about how the sun works. It's a good question, actually, because we still don't know quite the answer to that, all joking aside. We know that the sun has this 11-year cycle that's all to do with magnetism, but we don't know the root cause of all this. So I think we can forgive Dave Cleary for that one.
There is some thought that there is a meridional north-south transport of material kind of sinking down near the poles and then traversing back in the other direction around the tachocline region in the sun that takes place over 11 years. But
is that idea still flying? Because I remember reading about that in a paper years ago. So obviously it's still ongoing.
It's just a correlation, but
yeah,
I think that idea is still alive. Yeah.
Good. Let's hope we can.
Of course, there's also longer cycles.
Yes,
of
indeed.
the sun, which last decades. And of course, we're talking about the 11-year cycle. Now, that is a average, because some cycles have been as little as 9 years, but others have been as much as 14 years. So they basically even themselves out.
Yeah.
And really, in theory, I prefer to say that this is if you're using averages, a 22-year cycle, because to get back to where it was originally when it starts its first cycle, it takes 22 years. So yeah.
Okay, so moving on. Next, Einstein. This was in response to a post by a heliophysicist talking about the solar activity. Somebody disagreed with heliophysicists and said, false teachings from fools and demons. So obviously not a very high opinion of heliophysicists there.
Who are you calling a demon?
Yeah, exactly.
I accept the fools, but not the demons.
Yeah. And the most worrying thing about this is that it's posted by somebody called John Bletcher Sr., which means there's a John Bletcher Jr. as well, probably. That's even more frightening. So there we are. Somebody talking about the solar wind. UK Birmingham Erdington had some wild wind yesterday. Stay safe all.
Okay. Yeah.
Slightly different.
Yeah, somebody not quite understanding what the solar wind is. Also on the solar wind, is it tugging on all our volcanoes? That's what somebody wants to know.
Well, that actually is a question that's asked quite often, and the same with earthquakes.
Yeah.
Is there a correlation? And the jaw is out. There's no proof saying it is, but there's also no proof saying it isn't. I mean, if you look at the moment, I mean, maybe it's a coincidence and people look at these things, but we've got quite a few volcanoes kicking off and have done for the last 2 or 3 years. And we've also had some extensive volcanoes, earthquakes as well. So is it or isn't it? We don't know. So that is a true question, but I don't think it's actually tugging on them.
No, and it's difficult to conceive of a mechanism where the solar wind, which doesn't reach the Earth's surface,
no,
has any effect on volcanoes or earthquakes. What the mechanism for that would be, I don't think anybody could say. It's certainly not.
Thinking has to do with a reversal of piezoelectric effect and electromagnetic currents that could destabilize or kind of grease the region between fault lines.
Yeah, fault lines.
We don't know.
All that, yes.
Yeah. Next one, I've just called Jesus. I wondered why I feel like I'm having a huge brain setback. This is about the solar activity. Ouch. I pray for everyone suffering with these awful solar flares and be encouraged Jesus is coming back for anyone who believes in him before God's wrath comes, which is near. So now you know. So solar flares and Jesus the inevitable association.
I'm sorry she's suffering. Perhaps
Perhaps
it will help with tutor good.
There is a research going on into whether or not people are affected by solar flares and CMEs, because there seems to be a possible link with people suffering headaches, nausea. Some people with implants have problems. And so there is a thought now that maybe some people are susceptible to. It's like some people are susceptible to thunder coming. They can feel it long before anyone else. They get migraines and things like that. So I don't know. It's a thought, but the rest of it, okay.
Yeah, absolutely. But there's always one. Whatever happens in the universe is down to Jesus. So there we are. I've just called the world whatever. It all has cosmic relevance in planetary, psychic, physical, quantum, geo-astrological impacts. So now you know.
That's what I say. Yeah, I agree.
Yeah.
Does anybody know what that means?
I've got it for a while.
Yeah.
That's your homework for this week, Michael.
Yeah.
Find out what this means and explain it.
Yeah. Yeah. And,
the answer's 42.
Yeah, of course. And another whatever. Actually, it's the same person. Solar flares cause planetary stress due geomagnetic reactions in our magnetosphere. It's unrealistic to doubt the many influences upon our environment as mere superstition or fringe science. The probabilistic outcomes change instantaneously with thought, and larger forces beyond our realization down to the mundane, like your cup of Nespresso or Einstein's shadow.
Okay.
This is interesting because you started reading this. Solar flares cause stress due to geomagnetic reaction. Okay, yes, that's true. And then as it went on and on, it just got less and less palatable until it's talking about my coffee. So it grabbed me and then threw me down.
Yeah.
I mean, we've had a couple here this week which start possibly sound as though they're going to be sensible, then they just dissolve.
Yeah. Okay. And so that brings us on to this week's Einstein of the Week. Listen, I was killing myself laughing over this one, and I'm sure you will do as well. It's short and sweet. Here we go. Einstein of the Week for June the 3rd. An aurora hit my window yesterday.
Didn't break it.
Okay. Right.
Oh dear.
She must be on a very tall mountain.
Yes, indeed. So there you are. So
Samuel just says, "I'm just confused."
Yeah.
You're right. You're right there with the rest of us, Sandra.
Yeah. Anyway, that's Einstein of the Week for this week. Hope you enjoyed those. There'll be more next week, I'm sure. So there we are. All right. Where do we go from here? Right. So I think that nearly brings us to the end. Daz, did you want to say anything about solar activity, or shall we do Constellation of the Week first? Up to you.
Well, we could do Constellation of the Week. Well, actually, just because we've just done the sun, actually, what I'll do is if I quickly do mine.
Okay.
And then what we will do is now let me get this right. I've got a share window. That's the one I want. Share. Right, because this is actually linked to what we were talking about in the Einstein of the Week. And this is on Friday / Saturday morning, literally on the midnight. An event happened on the sun from AR 4100, and it was an M 8.2 flare. Now, as we know, the M means medium. It's not a big X flare, but the reaction that actually came from this is basically the sun literally pulled its face off. It really was. and it was supposed to. It hits. We did get solar storms, but we'll talk about that in a second. So I'm assuming you can see my cursor because I'll need it a bit later on. Yep. Anybody there?
Yeah, that's great.
Right. So let's start again. We were talking about the the cycle. It's now presumed by most experts now we are in the decline. And as you can see, last month's figure, which is here, did actually drop right off. This was last August. These are monthly totals. We thought we were going to pick up again, then it slowly dropped, and it's just jiggling down. So they now think that we are on the decline. But this is the predicted decline of the sunspots. How many sunspots are on the face of the sun? But it's dropped well below this time. So it'll be interesting to see whether this goes. Does it mean we're going to have a short decline? Or are we just going to pick back up again and then slowly fall down this slope? Something to watch out for. Now, because we are past the peak, presumably, as Lou said last week, we do tend to get double peak cycles, which will give you sort of like a profile of a volcano, because it'll pick up again and you'll have a sort of like a crater, and then it'll come down the slopes again. We've just got to wait and see, because if this carries on really fast, means we're going to end up with a very, very short cycle. As I said, 11 years is just an average. It's not actually written in rock. So that's just an update on where we actually stand on the cycle. Now, this is the sunspot that gave us all the fun. AR 4100. It came onto the on the eastern limb about sort of like 7 days ago, and it's been moving its way across, and you can see how it's changing, and it's getting larger, and it's actually, more parts are forming around it. You've got lots of mingling, lots of things going on, which it means we're going to get. I mean, it was given us a lot of activity before it actually came on the eastern limb. So we were expecting some big stuff from it, and it has been firing off low class stuff, C flares, and some lower M flares. But what actually, so if I carry on, this is it. You can see it here. This was taken a couple of days ago, and it had a mix of the actual beta, gamma, and delta. That means that the north and the south pole holes in these spots are mixing together, and once they mix together, they don't like it. This is when you'll get your flares happening. So we definitely knew it was so this is in white light, and this is sort of like a magnetogram image. And you can get all of these. They're easily accessible if you know which of the sets are. This is Solar Ham. You'll find these sort of pictures on Solar Ham, this one. So that's what we're looking at. This is the culprit. And as you can see, at the moment, it says no worthy events. M45, which is a medium class flare. Then we had the M8.2, and we also had the M3.4 on the same day, but earlier. And I'll be talking about this. So this 6.13 actually set things up for what we were actually talking about. So here we are. Again, here's the list of flare events. And if you look, the big flare player over the last 48 hours of when I took this image, it was, and this is going back 2 or 3 days now, you can see it's M4100. All the time. He's been the player, and this is where most of everything that's been happening has come from this week. Now, what we had, and I've got to sort of like preempt this. If you remember, I said there was a flare 6 o'clock on the 30th, 6 o'clock in the morning on the 30th of May. And this happened, I'm using my cursor because it was hard to find an image of it. It happened in this region here. And what it did is it came down where my cursor's coming. It interrupted, but this is a black hole. This is a black hole. This is a coronal hole here. You've got a coronal hole down here, which you'll see an image of a bit better later on. But you can see these filaments all the way down here, these dark filament lines, and they come across over here. Again, just above, starting just above, this is AR 4100. If you look, there's filaments all the way around here, down just actually on the side of this black hole where the dark area is. You'll get a better image of it later. Now, this is just before the eruption, and again, as I said, this happened at literally it was at 12 o'clock. It was at midnight that this actually happened. So it spanned 2 days, and it was a long-lasting one. It was an extended event, so it went on for quite a while. And so what we got there, so you can see it there. Now, I'm going to play these backwards and forwards. Can you see the flare has gone off? It's brightened quite a lot in here, but you can also see all down here and here, it's all lit up. And this is where the actual filaments have started to lift off. This is your coronal mass ejection. So we got the flare, coronal mass ejection coming off through here. But also, it's also, like I said, 6 o'clock earlier, we had this other one go off, which lifted off some filaments from down here. And what happened is basically this whole area over this period of 18 hours completely lifted off the sun. And look where it's looking directly at us. So it's coming, and it was literally directly at us. As I said, you've got a black hole here, you've got a black hole here. They're going to add to how fast these things are moving, because we get the enhanced winds from them. And also, these are negative polarities, these black holes. And if you remember going back, I remember SNAP, spring negative, autumn positive. This is talking about the equinoxes. The closer we are to the spring equinox, for some unknown reason, negative polarity coronal holes interact with us, then the positive do, and then the vice versa in the autumn. So as you can see, it's gone off. All this is lit up, and it's actually showing you what's going on. There will be some animations coming in a little while. So let's have a look. So this is what happened with the actual flare at the time that the flare happened. Remember, it takes 8 minutes for the magnetic storm to come and interrupt with the radio flares. Now, as you can see, the day side is on both sides, the colored parts and all that. So these are the parts that have been hit. And look at what the colors they come. We're coming right up into the greens, almost into the yellows in the center. You can just see the centers are up in the level. So we're right up here. That's the absorption. So these areas suffered great radio blackouts. It's an R2 level radio blackout. And on the right-hand side, you can see 4100 actually firing up. And you can see when it goes off, if you just watch it, you can see all around here again, this all lighting up again. So this is what people were on about. Now, this was going to create a big storm for us, and we knew it was going to come. But because there had been events before, we knew this one was traveling very fast. But because we knew there had been events before, plus also because everything went off together within such a short period, there was also what we call stealth eruptions, stealth CMEs, where we can't actually see them lift off. So we know that they were happening because we saw the filaments dissolving and things like that. So they knew they were coming. Well, this here, this is the warning up the top. KP index 8 or 9 threshold reached on the first. Now, we were expecting this. The prediction was that this was going to hit us June the 1st at around about midday for us in Europe, UTC. But as you can see, it actually hit us 4 hours earlier, which basically means that this was traveling really fast. Within 24 hours, it hit us. Now, as we know, and I've told you before in the past, CMEs take generally, at least if they're fast, they're usually about 2 days. But if they're just normal, plodding along, they take 3 to 4 days, sometimes 5, to actually hit this. But this came in, and you can actually see in this box at the end here, that is the impact of when it actually hit us. You can see all of a sudden, all of these graphs suddenly shot up as it actually slammed into us. There was a bit of concern that we'd get some sort of like a EMP to a certain extent, but it didn't really happen, because what happened is this, even though it traveled fast, all the stuff that had happened before was traveling slower. And as I've said before, if you've got events that have happened before and you've got a fast event coming behind, it will push up against the others. It will squash together. They will not merge, because, like anything else, like magnets, they do not like to be together, unless so they will not merge, but they will bank themselves up. So instead of just getting a hit, saying bang, 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 they'll bank up together. And when they hit us, you'll get it be like a machine gun to go bang, 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 bang. And this is what we've had for the last 2 or 3 days. So now here's some videos. Now you can see that's a separate one, but you'll see the big one go off a little bit later. Bang, there it goes. And did you see that shockwave go all the way through there? That was the and you can see there's more coming off. There's more flares. It also affected right down into this black hole, this coronal hole here. Lots of material flowed down into it and created an ejection of some sort. But also, I'd like to point out, look at this big filament coming on the eastern limb here. Look how big it is. There's the Earth. Look at that. Boom. And you can see it's vibrating, it's pulsing, and things like that. Now, this is a different wavelength. So you'll see that again, you'll see things going off. So bang, there it goes. It actually opened up a big load of this actual coronal hole here. And this had been giving us lots of wind, enhanced wind, the week before, plus all the other CMEs have been going on. And again, you possibly saw this going down here. Again, look at this filament. It's twisting, it's bubbling, it's boiling, and it is huge. It's another big one. And you can see things are still kicking off here at the moment. So and here's again is another view. This will give you the intensity of light. You'll see a shockwave go there. And then just after it's done that, look down in here and you should see it just boom there. There's another one gone off. And again, you've got all these other CMEs, just flares kicking off, and they're adding to what's actually already coming. Now, this is again a wavelength. Now, watch it. It's gone off. This one was a bit later. It's gone off. And look at although the whole thing, this is what's actually closed it up. When you look at other images, it looks like that actually was the black hole that was exposed. And as you can see, the only reason we can't see the black hole or the coronal hole now is, remember, this is a sphere. It's not flat. It's a sphere. So we're now looking at an angle and we can't see the extent of that black hole. We can just see a bit at the top. But again, this one's coming in and this one's going to be a player. But again, look at these filaments. Now, if anything happens here now, we're not going to get a massive display because basically it's wasted all its energy and we'll go. Now, this is a magnetic thing. You can actually see how it's been nicknamed the zipper. As you can see, it opened all this up. You can see all this stuff flowing down. So this bang, there it goes. And it opened up all the way down through here. And basically we got virtually, probably 3/4 halo from this thing. So we knew it was going to come and hit us. So this is for the UK. And this is the KP index, remember? And remember, each of these bars is 3 hours long. So this is how it hits us. But if you look here, we were all, because of all the pre-events that had happened, back to the 27th, the atmosphere was already being shaken, and it was ringing like a bell. It was unstable, so that when these things did hit, we were in for possibly a very, very good show. But there was a problem. Look at the times that these things actually arrived. Most of them arrived during the day. So for us, there was nothing to see. I actually took this a little bit earlier on today, and we were still ringing. But now I've looked just about 10-15 minutes ago, and we've dropped right back down again to sort of like base levels. But even today, we were getting auroras. But unfortunately here, because and another thing here is when these happened, literally with the BZ, which is the magnetic part of the sort of like in our atmosphere, in our magnetic sphere, was positive. Was north, so we didn't get anything from it. But it did drop down to the south. But of course, that was during the day, and unfortunately for me, when it came up here, it was raining, so I couldn't see anything. And also, we've got a very bright moon at the moment. Now, what I'm quickly talking about is I've just told you these bars are 3 hours long. So, but they are in the past. So when you see these alerts go off, that means that's what's happened in the last 3 hours, not what's coming. So you could have missed the main event. But I'm just going to point you to this. This is an HP index, and this called HP 30. Now this is measured in. This is produced in Germany, and each of these actual pillars is half an hour. So instead of waiting 3 hours, you can have a warning here, like here, say, oh, we've got an orange alert. Now let's go outside, set up the camera and see what we can see, and start taking photographs a lot earlier than it's telling you what's happened in the last half hour, not 3 hours ago. So it gives you more of a warning to that possibly if you know that something could be coming, is to get your camera out and have a look. So that was I just wanted to point that out to you. I just wanted to show you again, compare it to that's the 3 hour one. That's the half-hour one. There is also an hour one in between, but this will give you a bit more of a warning if you know how to use it. Once you get your yellow alerts or amber alerts, whatever you're looking at, then you will see these. You know that possibly there's something big's going to come. Now these did reach levels 8. When you're actually looking at these on site, when you put your cursor on them, it'll actually tell you the time and what the KP index actually was at that moment in time. And as I said, this is every half hour. Now, another advantage of this is that a KP index will tell you, it will take you up to a KP9, and then it will stop. Anything that happens above, it will just stay at a KP9. These will take you further up, so it will tell you exactly how big the actual storm was. So just a warning. So there we go. That's the KP index, which is 3 hours. Now here we go. You can see when it actually hit. So as soon as it all goes haywire, you know we've actually been hit with it. But as I said, here's the BZ. The things hit him. It just hits about here, and then all of a sudden we go north. It dips down quite a bit there, but again, it's still daylight when you come down. And then when you come up, we bit into the thing, then it's come down to the south. And it wasn't until sort of like last night, which is here, somewhere around here, that I would have been able to actually see something. Because again, it went up to KP8. So we would have had some sort of thing. I just hope some people were able to catch some. We weren't, but of course, in Australia and New Zealand, it's winter. And they've got the longer nights. So here are some. I'm just going to put, just to rub salt in the wound for everybody who missed it. Just put up some images that have been posted from people down in Australia, and of course they were also seen in America as well. But of course they're still sort of like in their summer mode. But these were taken from Australia, where they have the longer nights at the moment, and some of these are absolutely stunning. So. Yeah, we'd love to see these again over the UK. So, of course, these are southern hemisphere shots. You can see the the small and large Magellanic Clouds there. I think that's a plane. It's not actually a meteorite. The line just down there. And here's one that a chap did, and he said this is what you would have seen by eye. And again, you can see the Magellanic Cloud there. But this is that you could still see the pillars. So there you go. I hope that explains it. But we didn't get anything, unfortunately. But this is what all the fuss was about over the weekend, if anybody was hearing about. The only thing I would like, just one more thing I will tell you, if if you want to find out more about what's happening with the sun, I would recommend that you actually go and on YouTube and look for Tamitha Skov, Space Weather Woman, and she does a regular update of what's actually happening. So thank you very much for that. Thank you.
Thanks, Daz. Thanks indeed. So yes, Lou seems to have disappeared. Let's just resurrect Lou from being backstage. There we are.
Yeah, he'll eat all the biscuits.
Yeah.
And we know what he's like in the green room.
Yeah, I bet all the bottles are empty. So there we are. Okay, thanks very much. Michael has had to leave us, but he's on holiday for the next 2 weeks, so we won't be seeing Michael for a while. So we're going to go now, after that very interesting presentation about all that solar activity. We're going to go over now to our regular featured Constellation of the Week. And this week it's Roger doing the Constellation of the Week. And the Constellation of the Week is... Ophiuchus.
That's it. Yes.
The one nobody can pronounce.
Yeah.
Okay. So we've got Ophiuchus, which is the serpent bearer. It's currently visible above Scorpius in the southern skies at the moment. So it is quite a nice large constellation to look at, and it does have quite a few Messier objects. It's from the ancient Greek Ophiuchus. So there we go. So it's also been known as Serpentarius from the square of Pegasus. So it's been quite interesting to see how the names have been adapted over the times that we've been studying these. So the brightest star Alpha Ophiuchi is known as Razelhag.
Of course.
And is, yes. And it's roughly 48.6. So it's a binary star system of 8.62 years. So that's quite an interesting thing. It's got a mass of 2.4 times of the Sun. And it's a main sequence dwarf on its companion with 85% of the Sun's mass. So there's a 25 times more luminous between the major and minor stars there. So there we go. We then go over, for some reason, Eta Ophiuchi is the second brightest, but there we go.
What is that? What?
I don't know, but there we go. So I've been told by the information. So as we work our way around the main one here, we've got Zeta Ophiuchi, and that's 8 times the Sun's radius and 19 solar masses. So there are some quite large stars in this group. And this is what it's taken with the Spitzer Space Telescope. Right. Just to give you an idea of what it's doing. As you can see, it's blasting the gas away from its from the star there. So it's quite an interesting thing to actually be able to see, if you could, if you got a spare telescope like that. So we've also got some other brighter stars 171 light years away on Delta, and they're all quite large. So mass of 1.5 times of the Sun, 50 times the solar radius, and it can be quite.
So these are all huge stars, aren't they?
These are all quite big stars, and we thought the stars in Orion were quite big, but these are sort of on a par to the belt stars as well. So it's quite interesting to find out these things. I mean, and this one's 11 times solar mass as well. So there are all quite large stars. I mean, Ophiuchus isn't a lot. Not well known as a lot of the other constellations, but it's worth a note and looking at, especially when we find out what there are in there object-wise. So we've got 7 Messier objects in the constellation. So it was obviously worthy from for all these constellations here. So we've got IC 4665 Colander 349, which is an open cluster, and that's roughly 1100 light years away. It is easily visible with a small telescope or even binoculars, and that is it there.
Lovely. Sweet.
Oh,
Yes.
very nice.
Open clusters aren't really my cup of tea, but there we go.
You open
Somebody's got to love them anyway. So we've then got another large open cluster, NGC 6633, and it's also been known as the Tweedledum cluster, paired with IC 4756, which was the Tweedledee. So some quite interesting ideas for naming these various subjects. And then I've just randomly put the markings out for the Messier objects, which are spread throughout the constellation here. So these are mostly globular clusters. So if so they seem to be quite rich in globular clusters in this area. And if I do that, you can see all the different ones here. So it's quite interesting to see how they compare color-wise with blue stars and yellow stars.
That M10 looks very much like M31, M13, doesn't it?
M13, yeah.
Yeah, or M3.
I mean, M12 looks M12 and M62 look very orange, which you would expect, because as we said last week, these are the ancient stars.
Yeah.
But they're interspersed with blue stars, which are what, as I said, they're called blue stragglers.
Yeah, that's right.
They're lovely. I like globular clusters.
Yeah.
I like globular clusters too.
They're sort of like the fanboys.
So, but the more famous and most interestingly coloured object is the Rho Fucae Nebula, which isn't too far away from Antares in Scorpius. Right. So if you use a fairly short focal length lens on a camera, you should be able to get a stunning display of that area with also M3, which is quite close to Antares as well. So if I put that on, this is what.
Lovely.
Look at that.
That's amazing.
And you can see M3 there above Antares there in the golden clouds there.
Beautiful.
Absolutely. Yeah.
Wow.
It's one that I've always wanted to try and do, but it's always a bit of a challenge from the latitudes here, because it doesn't exactly rise very, very high in the sky, and you need a good southerly horizon to be able to get a decent one. But even just using an 85 or a 135 millimeter camera lens, you can get some absolutely amazing field images of this, and then be able to get all the details and all the colors of the objects that we have here.
You ought to bring your camera gear over to Spain, Rog.
So just because I visit Andy.
Yeah, that would be good.
You'll also see.
So that concludes the constellation.
Thank you very much.
Thanks for that, Rod.
That's
yeah, if you go and visit Andy, you'll also be able to view that different sun that they've got.
Yeah, that's right.
Yeah.
The hotter sun. Yes, absolutely.
Yeah. The hotter sun. Yes.
And with summer here has kicked off remarkably early. So we're looking at temperatures around in Fahrenheit 85, 86 that we've had the last few days, which has been a bit uncomfortable, and very high humidity we've got at the moment as well. It's absolutely punishing. So there we are. Not that I'm complaining, of course, because I wouldn't. So there we are.
85, 86 degrees centigrade?
No, Fahrenheit.
No, Fahrenheit.
So, thank you for clarifying that. Okay.
All right. Yeah.
You guys use Fahrenheit. Okay. Yeah.
I said Fahrenheit for you, Lou.
No, you're the best.
I know. So there you are. Paul says, thanks, Roger. Knew nothing about that constellation. Some images included really helped to show the majesty of what's there. Absolutely, Paul. Absolutely beautiful.
That's good.
Beautiful. But
Roger,
what surprised me was the high concentration of those massive stars in that constellation. I mean, they were big.
Big stars and lots of globular clusters.
What more could you want out of life, eh? So
absolutely.
You know what I like most about Ophiuchus?
What's that?
It is the 13th constellation in the zodiac.
It is. It is.
So for all of those astrologers
I didn't want to mention that.
working with their 12 constellations, I'm sorry.
And what that means is effectively that if you think your star sign is Virgo, it's actually Libra, and so on. Because thanks to the wobbling of the Earth's axis called precession, since the original zodiac constellations were established, there are now actually 14 signs of the zodiac.
What is the 14th?
Yeah, I can't remember what the 14th is, but this fact is conveniently ignored by astrologers who insist on their 12 zodiac constellations. But there are, in fact, now 14. If I'm right, I'm pretty sure there are 14. If you want to look that up, but Ophiuchus is definitely the 13th sign of the zodiac.
I didn't want to mention that.
Why not? I think they ignore it because who the hell wants to be born under the star sign of Ophiuchus? So
you're too nice a guy, Roger. You're just too nice.
Melissa, it still is the 13th sign of the zodiac. Not used to be. It is the 13th sign of the zodiac.
As long as it doesn't affect Sagittarius, I don't mind.
What do you like? What do you like? So anyway, all right then. So listen, now is your last chance. If you would like to, if you've had any further thoughts about what you'd like to see on the channel over the next year, any feedback at all, it's your last chance to put it in the chat. Thank you for your ideas and comments so far this evening. We will have a look and, as I said, digest and cogitate and see what we can do. Ophiuchus stands for the one who holds the dragon. That's right, the dragon bearer, indeed. So thanks for that, Melissa. Yes. So we'll start winding things up for this evening. Don't forget, we'll be back on Thursday evening, just before 7 UK time. I'll create the live stream tomorrow, so you'll see exactly what time we're going live. But join us on Thursday evening at around about 7 UK time for the landing of the Resilience lander on the moon. And please, let's hope this lander lands safely, because there have been a few failures over the last couple of years. So there we are. And if we don't see you on Thursday, we will see you back, as always, next Tuesday at 8 o'clock UK time here on the Space Oddities channel. Thank you so much for your donations this evening. Much appreciated, as always. Don't forget the Space Oddities website at https spaceoddities.space. And we will see you back here. There we are. There's something I didn't know, Alan. Both the Jewish and the Islamic calendars have 13 months every 3 years. That's Ophiuchus. There we are. Thank you. That's really interesting. So now we know. So we'll see you back here. Have a fantastic week, everybody. I hope the weather stays good for you. Whatever you're doing, have a fantastic time. Take care of each other. So from all of us at Space Oddities, have a fantastic week. And we'll see you this time next week. And thanks for being here. Bye.
Yeah, bye.
Keep looking up.